inverse. We already do this one. No.
This is section 8. We wanted to do it yesterday, but
I don't remember. This is like inverse.
a lot of questions. Huh?
Oh no, I was thinking, okay, never mind.
Inverse trig.
Inverse. I was thinking like the inverse of like cosine. Oh no. Yeah.
Okay. You see there are 5 bullet points here. Once we get started, it's a slow start. Once we get started, it'll go pretty fast. First thing we got to do is talk about derivatives of inverse functions in general. Okay, this takes a little bit of time. I'm on page 165 for anybody who wants to get there. Just a little blurb here at the beginning. I kind of like the way he says it better than I do, so we're going to read it together, and I'm going to comment on it if I feel like I should. So in section 1.5, we didn't even do chapter 1, so just pretend in previous courses, we learned that the graph of the inverse of a function can be obtained by reflecting the graph of that function across the line y equals x. That sound familiar at all? Okay. If we're doing a graph, looking at the geometry of it. If we combine that with our understanding of what makes a function differentiable, that might be a little bit fuzzy, we can gain some quick insights into the differentiability of inverse functions. And I disagree with the quick. It's going to take some discussion. Okay, so in figure 3.52, I want you to look at that. While I'm reading this, I want you to look at that figure. Somebody who had your book before, you may have drawn some things in, leave them there, they can be useful. If they haven't drawn them in, you may want to when we get there. This figure suggests the reflection of a continuous curve with no cusps or corners will be another continuous curve with no cusps or corners. Amazing, because all you're doing is flipping it over a line. Indeed, if there is a tangent line to the graph of f, I get this is going to, you have to think, we're going to go slow here. If there is a tangent line to the graph of f at the point a, f of a, are y'all looking at that? Then there will be a line reflected across the line y equals x to become a tangent to the line of f inverse at f of a. Because when you do an inverse, the x's and the y's reverse. They change places, right? Okay, so if we keep that point solid that we're talking about on the original function, a f of a, then that very same point becomes f of a, and there will be a tangent line to that also, but it won't have the same slope, as you can see. You wouldn't expect that. Unless the slope was at 45 degrees in the first one, which is rare. Anyway. We can even see geometrically that the slope of the reflected tangent line exists and is not 0 will be the reciprocal of the slope of the original tangent line. I'm not sure you can see that or not. Since a change in y becomes a change in reflection and a change in x becomes a change in y. They're switching places because we're talking inverse.
Quick question.
Okay.
You teach the remainder theorem.
I do.
It's taught in the Algebra 2 division section.
Yeah, I do. I don't put a huge amount of emphasis on it, but I do tell them it's a...
Because it tells you to evaluate for a certain number. It's like you just plug that number in.
Right.
Just wonder if it's valuable for them down the road.
No, it's not.
No.
It's not. You can always just plug it in. If you don't want to teach it, you don't have to. It's not a big deal. It's very minor. Okay. Okay, so let's go back to the last couple of lines here. It says, we can even see geometrically that the slope of the reflected tangent line will be the reciprocal of the slope of the original tangent line. Since, and the reason why we believe this is because the slope of a tangent line is rise over run, where the slope of the tangent line on the other one's going to be run over rise, because x's and y's switch places, and they're reciprocal. Does that make a sense? And so, if you can see in the first graph there, that's the graph of f, that red tangent line appears to be pretty steep, rising to the right. The tangent line on the one next to it appears to be just as, I don't know if the word shallow is right, but it appears to be just as not steep as the other one was steep, but still rising to the right. Because the reciprocal of a positive number is still positive. So don't get confused with this opposite reciprocal business for perpendicular. That's not what's going on. It's strictly a reciprocal. So that if the tangent of the red line in the first one is 3, then the tangent of the other one will still be positive, but it will be 1/3 in its inverse. Okay. Now, this little bit of this theorem down here is going to require some slow and meticulous hard thinking to get it straight. It says all of this serves as an introduction to the following theorem, which we will assume as we proceed to find derivatives of inverse functions. Although the essentials of the proof are illustrated in the geometry that we just looked at, a careful analytic proof is more appropriate for an advanced calculus text. We'll omit it here. So you will have to take the idea that we're about to discuss here as truth based on the geometry rather than our proof. Most people are okay with that. So here's what it says. If f is differentiable at every point of an interval I, okay, so on interval I says we're only going to look at this function from a to b, and that's it. Now, we don't care what happens on the outside, it's just a to b. And that's our interval. What the interval from a to b is called I, an interval. Got it? Okay. If it is differentiable at every single point in I, and the derivative is never 0 on I, then f has an inverse and is differentiable at every point on the interval f of I. In other words, the interval on the y-axis now. It was on the x-axis for the original, now that interval is on the y-axis, which is called f of that interval, the y value at that interval. You with me? But listen to this part right here. If f is differentiable at every point on the interval, and the derivative is never 0, why is that important?
It'll be running slow.
Yeah.
It'll be
Very good. Because the reciprocal of 0 is undefined. What's another way of saying, and the derivative is never 0?
It doesn't turn on.
Yeah, there's no turning points. It has to be rising or falling through the entire interval. It has to be increasing or decreasing through the entire interval. That makes makes the derivative never 0. They could have said it that way too. And is always increasing or always decreasing in the interval. You can be waving around all at once, but it's got to continue to go up, 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 or continue to come down, down, down through the interval. Otherwise, this doesn't hold at certain points.
Oh, through the interval.
Yeah. You follow what I'm saying? There can be no turning points. There can be no change in increase to decrease or vice versa. Here's another thing that I'd like to show you that's not mentioned here. That's further evidence that the reciprocal, that the two slopes are reciprocals. Consider this with me for just a minute. This is a little study in notation. It says if g is the inverse of f, so we have a function f of x, and well, I don't like that.
Where is this at? Sorry.
It's not in the book. It's further evidence that I've got for you. So just watch up here. We've got a function f of x, and we have a function g of x over here that is equal to f inverse of x. So g and f are inverses of each other. Okay, that's how we're going to define the two. And I don't know if you recall this. We did do it when we were in Algebra 2 and in pre-calc, but a lot of people don't remember this. Since f and g are inverses, we know this, that f composed with g is equal to x. Also, g composed with f is equal to x if they are inverses. Just as a side note here, that might help you on an ACT test, get you a quick answer if you'll remember this, I don't know. If you compose f with its inverse, you get x. In other words, f composed with f inverse of 4 is 4. You don't have to try to find the inverse and evaluate it and then function that value and get 4. They undo each other. You get what's in here every time if they're inverses.
Arc sine and like sine. Yeah. Like in the
Oh, yes.
or something. Like
If it's in the correct order. Yeah. Okay, so they kind of undo each other. When you log an e to the x, you just get x. It's the same idea. Inverses undo each other. So if f and g are inverses, and we compose them, we expect to get x. Do you agree? What is the derivative of both sides of this? What's the derivative of this side? Okay. Oh, that's not what I want to do yet. That's going to get there eventually. So I got a 1 here. I got a 1 here. What's the derivative of this side? That is the heart and soul of the chain rule, right? Yeah? Which means that, algebraically speaking, that g prime of x is equal to 1 over f prime of g of x. In other words, f at g. In other words, I guess what I'm saying is g of x is an x value. F of that value is a point on f. And its slope is this. Well, slope. What I'm saying is the slope of g at that very same x is the reciprocal of f at that same point. That's more evidence that the reciprocal thing actually works. The slope of g is the reciprocal of the slope of f at the same. And you go, but what about that g of x thingy? Well, remember that a point on f is a f of a. That's a point on f, but a point on g is f of a. There's your f of a. G's and f's mixed up, but this is the y value that used to be the x value on the previous one. That's all we're on. We'll see if it helps, because the very, very next exploration that we're going to do has to do with this theorem, and you may want to refer back to the details. Let's look at it one more time. If f is differentiable at every point in any interval I, and the derivative of f is never 0, that means, and you've got to be able to interpret that, means it's always increasing or decreasing on the interval. Then f has an inverse function and is differentiable at every point, so long as the original one is always increasing or always decreasing. Now, let's see if we can apply this. Try this exploration. We have f of x equals x to the 5th plus 2x plus 1, or minus 1. Let's put that up here. 5th degree polynomial. Pretty crazy. Tell me what it was again. F of x is equal to x to the 5th, is that right?
Yeah.
X to the 5th, and then?
Plus 2x.
Okay, so that's f. 5th degree polynomial, well behaved, has a derivative everywhere, but has some turning points probably, right? So we're going to let f be that. It says since the point 1, 2 is on the graph of f, is it? Is the point 1, 2 on the graph of f? You put 1 in for x, do you get 2? Yeah? Okay, so we're convinced 1, 2 is on the graph of f, so that's a point we're going to consider. So f of 1 equals 2. That's what we're going to say there. That's a point on there. Okay, and then it says, it follows that 2, 1 would be on the graph of f inverse. That make sense? And so from this, we get that f inverse of 2 is 1. That's the same as saying 2, 1 is on the graph of f inverse. We good? This is like saying a f of a and f of a on the previous one. We're making it specific. Can you find the derivative of f inverse at 2? Do you know what f inverse is? Do you know what the function f inverse is, or could you find it? Could you? I bet you couldn't.
There's 2 x's.
One's 5th powered and one's single. Do you remember how you go about actually finding the function f inverse? You remember that you switch places with these?
Yeah. 2
And then solve that thing for y?
Yeah.
Can you do that?
Yeah.
Really?
No. Polysymbols. Yeah. Easy peasy.
No, solve for y.
Yeah. No.
Polysymbol. No.
No, there's one.
Polysymbol finds the zeros of this.
I gotcha. There's
What?
two Y's. You can't. Okay, isolate the two Y's, take a Y out of it. And now.
That's what I thought.
Wait, I'm not done.
You keep working on that because I don't think you can do it.
Ouch.
Okay. So it seems like to do this directly is impossible. And it is to do it directly impossible. Because you can't take the derivative of f inverse if you can't find f inverse. You can't do it directly. But there's still a way to find the value of the derivative of the inverse evaluated at 2. There's still a way to do it without ever knowing what f inverse is. Don't sit there and look at me and tell me I think I'm going to explain it to you. Let's see if we can understand the problem, see if you can think a way to figure this out. We cannot find f inverse. We cannot solve for y when we switch places with x and y. That's usually how you go about finding an inverse. Then you resolve the thing for y. And yet we are supposed to evaluate the derivative of the inverse, which we can't find, at 2.
Could we find the derivative of the original at 2 and then just the reciprocal of that?
Swap places.
So you want to find the derivative of this function here. And
At 2.
evaluate it at 2.
And then is the reciprocal of that the derivative of the inverse at 2?
That will not be correct. But it's a good thought. It's a way to progress. That would be the only flaw in his plan. So tell me how you would fix it.
Wait, would we use implicit derivative?
What?
Still switch x and y places and then write that. Leave it there and then plug it. How would it work? Yeah, I know that. So would we still switch the x and y as find the implicit derivative for that? And then
I don't think implicit's necessary though. Because we have y in terms of x. It's just a polynomial.
So we're just trying to figure out how to derive this, right? That's all we're trying to do.
you're right.
We're trying to figure out the value or the slope of the inverse function when x is 2. On that
Why don't we just
function.
derive that one, find what it is, and then invert that?
Just reciprocate it?
Yeah.
That's just what he said, and that would be incorrect.
Why? Explain that.
No, I don't want to. I want you to figure out.
Wait, but no, because they would just reciprocate over. You have to put a negative on it, but.
No, you don't have to put a negative on it. That has to do with
Does that have-
perpendicular lines.
Does it have something to do with the...
So what if we find the derivative of the first function at 1?
Then tip it over.
That's
The
what I
only
said.
flaw is we don't want to evaluate that derivative at 2. We need to evaluate it at its x value before we flip it over. That's what you were getting to, but you couldn't quite put it together.
Is that because the inverse is differentiable at every interval? Half of...
Wait, I don't
You just do, that's what I.
That is not what you said. I was listening
What did I say?
carefully.
What did
Sam?
I say?
Sam, don't.
That is not what you said. You said just what he said,
Yeah.
which was close.
What did I say? Here's some.
You said we should find the derivative of this and then plug 2 into it and invert it.
I didn't know what plan we were talking about.
I don't know why he was even talking about 2 now.
All right, listen up. Shh. Let's see if we can find this. According to what Mariah just said, which was correct. Did anybody hear what she said?
Yes.
Yeah.
What should we do then? How should we proceed?
Find it hard. Derive it.
Okay.
Evaluate it 1.
5x plus 2. And then find that at 1, which is 7.
The inverse would be
1/7. No, yeah, 1/7.
wait a second.
Where did the 7
Wait a
come
minute.
from?
What's that?
Plug
When
one
you
in.
plug in one to the derivative.
You have to stay true to the point that is on F. So that means you have to evaluate the derivative at 1, and the reciprocal of that will be the evaluation of this one when x is 2.
That's not what you said.
That's what I meant.
Because they have to switch places.
I got it, okay. I was.
So this is x, f of x. This is f inverse of, this one's y, which turns into this one. And so you can't evaluate the first one's derivative at 2. You have to stay true to the point that's on him, on that one. Find that derivative value at that x that belongs to f, and that will be the slope of this one's derivative at his x, which was they flipped over when you reciprocate it.
It's so weird.
Isn't it weird?
Wait,
That's
so
very strange, and
what's
they
the-
love this on AP and final exams to be able to do this to you. And it's not hard if you know what to do. Which is to remember that the points have got to be flipped over. X's become y's, y's become x's, and so as long as you're talking about f, you have to stay true to the point that's on f. Then you can make assumptions about what happened to the point that was on f when you get to f inverse using a reciprocal, but you have to evaluate it at the point that's on f. Following?
Yep.
Pretty crazy.
Okay.
Okay.
Wait, why don't we just derive it as y's and then plug it in?
That's where I was going.
Switch places with x and y,
Yeah.
and then derive it implicitly and evaluate it at 2. Would that work?
I think
Oh,
so.
let's try it.
That just seems like.
Yeah.
Okay, let's try it because we like to investigate things here. So f inverse is going to be x equals y to the 5th plus 2y minus 1. And so the derivative of this would be 1 equals 5y to the 4th.
dy dx.
Okay.
Plus 2 dy dx. And then you isolate that, so you end up with 1 over 5y to the 4th plus 2 equals dy dx.
And that would be,
So it would have worked.
when x is 2, that would be
1.
Oh, so you plug in.
1.
Did you plug in 1 or 2?
yeah, because we've got to plug in y for what y equals
1,
1.
so it's 1/7.
Yeah.
Boom.
Oh,
That'll work.
Boom.
So you didn't actually have to solve for y and then derive with respect to x.
Yeah.
You can drive implicitly. Further evidence that what I erased up there is when I divided by f prime of g of x.
We should take a
So
whole
what's going on
day to just try to figure out how to solve with 2 different.
You go right ahead. I'm not spending time on that. Okay, now, that's,
Switch the one with that.
listen carefully. That's true of all functions and their inverses so long as it's constantly increasing or decreasing. And you know what? It's true of all functions even if they do switch increasing and decreasing, except at the point of switching. So if you've got an interval where you've got a maximum and a minimum, a local one, then what I just said is true for all areas in that interval except those x values. Because those horizontal ones would turn out to be undefined. So it still holds even if you got turning points on the places where it's not turning. The reciprocal will work. Okay? Now we want to focus the rest of the time because the title of the section is not inverse trig functions, or inverse functions, it's inverse trig functions. So we're going to focus the rest of our time and efforts on the inverses of the 6 trig functions. And those are functions themselves, and we have to derive those. Perfect. It'll be really fun. First of all, and I'm only going to do this for the sine curve, you're going to have to extrapolate it in your own mind for the rest of them. When you have just a regular old sine curve as the function, it starts here, well, it comes down here like this, and then it comes up here like this, comes down around, continues like that. Can you imagine flipping that over the line, y equals x, to find its inverse? Can you understand that that would be serpentine up the y-axis, and then would be a non-function? In other words, this y value goes from 1 to -1. If we switch places with there, then the x's will go from -1 to 1. And these have, this is 0, this is pi halves, this is 2 pi, no, this is pi halves. This is pi, 3 pi halves, and 2 pi, and then it continues on from there. That means that the things that are on the x-axis here, now on the y-axis here, we have negative pi halves, pi, and down here, negative pi. What would that look like with the sine curve if we just flipped it over line y equals x? Well, notice it starts at 0, 0, and then heads up toward a 1, so it's going to head out towards a 1 like this.
Yeah.
And then at pi, it's going to switch and go like that. It's going to come down like this, come out to negative 1 there, and switch at pi there. It's going to be serpentine like that. That's what they call that, serpentine.
That's weird.
And the inverse, I mean, the inverse of this, if we take all of it, is not a function. So we got a problem. What?
Does sine ever like go past that x line? Like that line?
A negative 1, a negative 1, a negative 1?
Well, like in between them though. Like if you just drew a line of x on that first one.
Oh, the line y equals x?
Yeah.
Yeah, what about it?
Would it ever pass that on the original one?
Pass it?
Like would, between 0 and pi halves, would sine ever be greater than x?
Greater than x. Yeah, probably,
Really?
if I'd drawn it right. Here's the deal though. We deal in functions in calculus. And so we're going to have to restrict the domain of this. Not the domain, we have to restrict the range. Because over here it would be the domain, this becomes the range here. So that we are looking only at a piece of this curve, and it could be any piece, but we're going to strategically choose it. So that
That is small.
it is a function.
Oh,
Check it out in your calculator. Graph inverse sine in your calculator. Make sure you're in radian mode. Make sure you're in radian mode and go zoom trig. Even then, you won't see much. So in your calculator, do graph inverse sine x in radian mode. It's really not really very exciting.
Wait, what are we doing? Oh,
That's
yeah.
Mine's a little bit more leany, but I mean, that's what you get. That's all you get. Because in order for inverse sine to be a function, we have to restrict its range so that it can be. That satisfies the vertical line test. If you extended it any further, it wouldn't. You understand this? Do you remember I told you before when we were studying trig that you could only look for inverse sine values in the first and fourth quadrant? Do you remember? On the unit circle, I said inverse sine, you can, if you're inverse sining an angle, you may only look for positive ones in this one and negative ones in this one. It only goes from pi or negative pi halves to pi halves. And voila, look, negative pi halves to pi halves. That's the only y values it's defined for. You can't look for inverse functions for sine anywhere else. Only first and fourth quadrant if you're thinking about the unit circle, or between here and here if you're thinking of a graph. Okay, now we could have restricted it to any piece that looked like this, but this seems the obvious one because it's close to 0. Goes through the origin. All right, so understand that restriction in inverse sine's range. You can only go from negative pi halves to pi halves. And can you imagine this curve right here? It does, well, I shouldn't have erased the pi halves up there, but this curve right here that we're looking at from, and I better back that down just a little bit so it matches my graph a little better. It comes up to here, this is pi halves. This is still kind of curvy, isn't it? In certain places, I mean, it's still, which means it has slopes. It has tangent lines that can be done, but only if we restrict the range from negative pi halves to pi halves. So if I tell you that I've got a function, y equals, inverse sine of x, that's a function. If we restrict it, what's its derivative?
Well, is it related at all to the derivative of sine? Would it be inverse goes on?
It is. It's got to be related some way or another. I mean, they're related graphically.
That makes sense.
Does it make make sense to you that if I were to sine both sides, I could isolate the x? Well, that's not really what I'm after. I don't want to isolate the x. That's not it. Does it make sense to you that if I signed both sides, I could eliminate the inverse sign?
Yes.
Let me remind you something about trig. If I sine an inverse sine of x, will I always get x?
Yes.
If I inverse sine a sine of x, will I always get x?
No.
That's true. This is true. This is not. We learned that in trig. Because you can sine anything, but you can only inverse sine certain things. So this one won't always just return an x, unless x is between negative pi halves and pi halves. If it is, it will return that. But if it's beyond that, if this is 3 pi halves, for example, then when you inverse sine that, you're going to have to find the angle that belongs to 3 pi halves that's in between here and here, and then inverse sine it. So this one doesn't always return, but this one does. This one always will give you x because you can sine anything. All right, so if that's true, then if I inverse sine both sides, we're pretty much guaranteed this, aren't we? And we've now turned inverse sine, which we don't know much about, into sine, which we know a lot about.
Something new a lot about.
So, do you all agree that this statement here and this one are exactly the same?
Yes.
Then if I can find the derivative of this, it's the same as finding the derivative of that. So, find the derivative of this. What do? There you go, Sonny.
And that becomes what? So it's 1 over, oh my gosh. It's secant. More secant of 1.
Do you agree with that?
Yep.
But what is y? I mean, the y dx that only has a y in it would be nice if it had x's in it instead. What is y again?
Sine of inverse sine of x.
Inverse sine of x.
Whoa.
Don't write anything down yet, because we are not done. Does that make good sense to you so far? Does that look like something? I mean, we just put inverse sine of x back into it.
But now it's more complicated.
Is it? That doesn't feel like something you really want to be able to do, right? Let me remind you of something else. Don't write anything down yet, Sonny. This is not done yet. You want to wait till we're done, and then you can write down facts. I'm not sure that's what I want to do. Instead, I would like to think about an identity having to do with this. And this is a tough identity because we don't often go this direction with it. But isn't it true that sine squared, let's use y because that's what we got here, plus cosine squared of y equals 1. Is that true? So that means that the cosine of y is equal to the square root of 1 minus the sine squared of y. Oh, did you buy that? It's really plus or minus. But now think about this with me for a minute. Look at the cosine curve, which starts up here, right? Just regular old cosine starts here, and it goes down like this, comes back up kind of like a dessert cup. Same thing over here. And this is pi halves, negative pi halves, and this is pi halves. So on the interval that we are allowed to look for inverse sine, that the interval that we're talking about right here, cosine is always positive, right? So the value of this, restricted to this interval, is always positive. So we don't need to look at this negative part of the plus or minus because in that interval, it'll never be negative. Would you agree with that? So I'm going to back off a step here. Instead of using inverse sine, I'm going to say, oh, because of my identity up there, I can replace cosine of y with the square root of 1 minus sine squared y. You're going, okay, that's kind of goofy. Do you see any place where sine squared of y could be replaced with something?
Yes.
In everything that we've done on the
X
board so
squared.
far?
X squared.
X squared, look. So, the derivative of y with respect to x, the derivative of inverse sine is what I'm saying. The derivative of inverse sine is 1 over the square root of 1 minus x squared. Very weird, very strange. The inverse of this turned out to not have any trig in it at all, has a square root of all things. It's actually kind of like Pythagorean theorem on this, but I'm not going to go there. I could show you that too if you wanted, but that's what it has to do with, is the slope of two legs. Anyway. So let me summarize for you what we've got so far. What we said is that in all of this work that we did here, that if y is equal to the inverse sine of a function, I'll call it u, you'll see why in a minute, then the derivative of that with respect to x is equal to 1 over the square root of 1 minus u squared du dx because of the chain rule. Now, if that notation doesn't mean anything to you, it will in the first example that we do. This is what you should write down, and it will have more meaning for you the more we see an example, several examples, okay? If y is equal to the inverse sine of some function of x, then the derivative of that is going to be 1 over the square root of 1 minus whatever this thing is squared times the derivative of that thing because of the chain rule. You following or not really?
Why did we use the chain rule?
Because it was just x and the derivative of x is 1. I was just showing you the simplest possible version of this, where this function that we're inverse signing is just, its derivative is just 1. Okay? But this could have been the inverse sine of x to the 5th minus 4x plus 2, and then we would have had 1 over the square root of 1 minus that x to the 5th minus 4x plus 2 squared times the derivative of that, which would have been a polynomial in the numerator for the 1. Okay?
Yep.
All right. So, with that in mind, let's take a look at the first example. It says, find the derivative of inverse sine of x squared. So this is our function, y equals inverse sine of x squared, and we're going to say that y prime is what? Now that we've done all of this grunt work here, we're going to have what as a result? Look at this.
1 over square root of 1 minus the sine of x to the 4th.
X to the 4th. Times? Times? Times 2x. The derivative of that. See it?
Yeah, I got it.
Okay, yep, chain rule. Chain rule there. Yeah. So whatever this thingy is behind inverse sine, you square it right there. But then you also multiply that 1 over thing times the derivative of that thingy, which is 2x in this case. Y'all follow that?
Yep.
Chain rule. Okay, now, let's see what we can do for inverse tangent. Following a similar strategy. So I'm going to leave this one up here. This was just an example. I'm going to erase it. Let's say that we've got y equals the inverse tangent function of, let's just do x for right now. We'll just leave it x so we don't have to deal with the chain rule. How are we going to find that inverse?
Do we start by multiplying the tangent like we did the sine?
Well, not multiplying, but tangent both sides. Yeah, we're gonna it's not a multiply. It's a different function. So if I tangent the left side, I get this. If I tangent the right side, I get that. By the way, where is inverse tangent defined? Does anybody remember from Trig?
All real. Or there's only from the range of like 1 to -1. We're not touching those.
Tangent is. No, inverse tangent would go from, well, think about that. What does tangent look like?
It's like that.
One branch of tangent goes from here to here. Asymptotic, right? Because it's not defined at those places and it goes like this.
So if we're-
What would that look like flipped over the line y equals x?
Yes.
These would have asymptotes here now, and it would look like that. So it is also defined from negative pi halves to pi halves. However, the sine curve includes those, whereas tangent doesn't. Because sine is defined at negative pi halves and pi halves, but tangent is not. So it's still in the first and fourth quadrant, but you're not allowed to look right at pi halves and negative pi halves for tangent. It's not defined there. For sine, you can look there, but for the most part, they're both defined in the same quadrants, first and fourth quadrant, or between negative pi halves and pi halves. Okay, that's where inverse tangent's defined. Okay, so now what? Just keep in mind where we're restricted, because it's an inverse tangent. Now what should we do? What's the general word for what you want to do? Derive. What's the other word? Implicitly. Okay. Secant squared of y, because that's the derivative of tangent times dy dx equals 1. So dy dx is? Then what did we do? Do you recall? Because I erased it. Then what did we do over here?
Use an identity.
Yeah, we used an identity. Now we need an identity involving tangent and secant, right? You think a Pythagorean identity would do any good?
Yeah.
Does anybody remember the Pythagorean identity involving secant and tangent?
No.
Find it.
Secant squared plus 1.
Look it up. Make sure you got the correct signs and everything. SIGNs.
1 plus tangent squared equals secant. Yeah, that.
Is that right?
Yeah.
So then I can replace this guy right here with 1 plus tangent squared.
Yeah, and then you can replace tangent squared with x squared.
And tangent squared is what?
X squared. X squared. Squared. Y squared on the top.
What? This is y here?
Yeah.
And then this is x squared, right?
How y is tangent square root of y accident?
So our general rule for this is, I'm going to erase this identity because it's kind of interfering with my list. If y is equal to the inverse, or is equal to tangent of some function of x, then dy dx will be 1 over 1 plus u squared du dx. Because of the chain rule. Did you catch that?
Yep.
Okay, be sure you get your SIGNs straight. That's a minus underneath a radical here. This is a plus sign without a radical. Both involve ones, but get your signs straight on these when you go to memorize it. But you will have to memorize. You will have to commit them to memory.
Already working on that.
So, here's the next example. A particle moves along the x-axis so that its position at any time t greater than 0, so only time moving forward, is x of t equals the inverse tangent of root t. What's the velocity of the particle when t is 16? Okay, I'm going to leave this up here as a general strategy. I'm going to erase this one. We're going to try to follow that same strategy the next time we do something, but I need this space to work an example because I don't want to move my computer in my ladder. So example 2 says we have particle whose position x of t is inverse tangent over a t. I don't need parentheses around that actually, but. And what we would like to do is find this particle's velocity at 16 seconds. So we need, we have to find the derivative of position to get velocity. So the derivative of position called velocity is going to be v of t, which is
Say go. I know. But that's our parallel. You know.
1 over 2.
Yeah. It's really yours.
yes.
Wow, that's
Oh, it's
not
getting
yours.
So then what is v of 16?
I'm dying right now. It's getting strong. I'm fine. That's why they just turned off the AC.
What's 17 times 8?
Big numbers.
136.
So he's still moving forward, but not very darn fast. At 16 seconds, he's going pretty slow. I hope those of you that were not paying attention followed that. Moving on. Guess which derivative we're going to find next?
We're gonna find.
We found sine, inverse sine. We found inverse tangent, not cosine. What do you think would come next if we did sine and then something as obscure as tangent next? Then we will do secant. Why? Because none of them have a co on it. We're doing the non-co-function. We're doing the non-co-function. So we'll do secant next. What?
Did Jacob come in today?
No.
Okay, thank you.
So I have y equals secant inverse of x. Now, secant is the reciprocal of what? Secant is the reciprocal of cosine. Where is cosine? Yes, excuse me. Where is inverse cosine defined when you graph it? Do you think? That's a serpentine thing too.
Yeah.
Where should we define that so that we get all the positive and negative values? Can you remember from Trig where inverse cosine is defined? Anybody? Good. Yep. First and second quadrant. Because with cosine, if you did it from negative pi halves to pi halves like we did with the others, all of your values would be positive since cosine's positive here. If you want to get all of the values in between -1 and 1 for cosine, you got to do first and second because cosine is positive here and negative here. So cosine is defined from 0 to pi. First and second quadrant. You with me?
Yeah.
Besides that, if you look at a graph of a cosine curve again, like I did a few minutes ago, comes down like this and comes down like this. If you defined it from negative pi halves to pi halves, can you see that all the values would be positive? But if you defined it from 0 to pi, you would pick them all up where this is pi. So we want to go from here to here. Can you see that inversing? If you took the line y equals x and flipped that over that line, you would still have a function if you only restricted it from here to here?
Yeah.
Because it's 1 to 1 from,
No, that wouldn't work.
yeah, that isn't right. From here to here,
Yeah,
that's pi.
that's good.
Sorry, that's pi. This is 3 pi half. So from here to here, if I flip that over, that would still be a function. Yeah? All right, so this is defined inverse secant because it's the reciprocal of cosine is defined on in the same regions from 0 to pi. How do we go about finding this thing's derivative? If we follow the same strategy we followed with the others.
We seek it itself.
Secant both sides? What's the process we're doing here? Deriving implicitly. What do we get?
Secant y and y yes.
Equals 1.
There we go. And now divide by tangent 1.
Cool. Like identities.
Is that it, or?
No, that's not it.
Oh, what is not it?
No. Well, your secant, it would turn into cosine, cosine line.
It's not necessary. Look around in the things that we've done. What is secant y?
So,
X. We only need a replacement for tangent y, which is what?
cosine line.
Square root.
Tangent y is equal to the,
Square root of 1 or secant square root of second.
like that? Does that look like a different version of the identity? Is that correct? So what we have now is that the derivative is equal to 1 over x square root of.
1 minus x squared. Oh, that's
And-
even cooler.
And you guys I can explain this to you if you want to take the time. But not only is it, in order to maintain this so that it is why would it be important that it be positive? That should be an absolute value right there.
Oh, yeah.
To maintain the positivity of this result.
You gotta have a positive function.
The derivative's got to be positive. Can you think of why that would be?
Because the regular functions.
It's a difficult thing to think of why that should be. What would secant look like? Inverse secant. Do you know what regular old secant looks like?
It's like that weird.
Yeah, it's related to cosine, right? So if cosine comes down like this, then secant has its scallops. It has asymptotes where cosine is 0 because they're reciprocals, and secant goes up like this, and down like this. And if it's only defined from 0 to pi, then you're only looking at this piece here and this piece here, right? Just those heavy pieces right there. That's all you get. What would that look like if you flipped it over the line y equals x?
That would look really weird.
Would it? So we would have,
It would start at 1, 0.
we have -1 here and 1 here. We'll go on those axes. This was -1 and this was 1. And so it would start over here at 1 right here. It would start and do what?
Go out like a square root. Go out like a square root.
Like that?
Yeah.
Start at 1.
Yeah, go out like a square root.
But there would be asymptotes. Would there be asymptotes? Yeah. At pi halves and negative pi halves.
Yeah, and then you start out.
So the asymptote would come out like this, and it would look like that. Is that what you're telling me? And what would this one down? What would that one look like?
I start up at 1, -1 pi. I don't think that's pi halves though. That might be pi quarters. Is it pi halves? Yeah, that's pi halves.
It's pi halves. Yeah.
Okay, so then start at pi.
We'll start here at 1 and go this way.
Pi. Start at -1 pi. Go to pi.
Up here.
Clear up. Further up.
Out here.
No, further up. To pi.
On the y-axis.
You're at pi halves. There you go, right there.
Oh. So I don't need those. That's going to be. So I need a pi up here.
Yeah.
And this is
-1
is this an
pi.
asymptote? No.
No, that's where it starts. -1 pi.
Oh. It would come down like this.
No, -1 pi.
Oh yeah. Right here.
No.
Right here.
Yeah, right there.
That would come down. Right. Yeah, thank you. Now that we have that curve drawn, what is the slope of that curve? All the time, positive, negative, sum of each? Always positive. Hence, the derivative of secant inverse must always be forced into being positive. Okay? That's why this has to have an absolute value on it. All right.
Wait, what? Oh, because it's always, okay, yeah.
Because the slope of that curve, when we do the inverse secant, when we finally get it drawn right, thank you very much, has to always be positive. And this will be positive because you can't square root a negative. But this one might be negative, in which case we would have to force it to be positive so the slope can always be positive when we're not talking about a secant, inverse secant. Okay, so Summarizing this one, we get the derivative of y with respect to x. Oh no, we have to get the y first. The y is equal to secant inverse of x. And so dy dx is going to be 1 over, I'm sorry, this is a u, is going to be the absolute value of u, square root of 1 minus u squared, d dx.
Well,
That's pretty crazy.
there's where you take it.
But that's only 3 of them.
Let's go. We don't have to go through this.
We're not going to do the others.
Oh, that's okay.
Because you're going to see something really cool here in just a minute.
Alright.
Oh, look. They drew the inverse secant curve at the top of page 168. Take a look at that. That's good that we worked on it together. You guys were right.
Did we do it right? Heck yeah.
Okay, so let's use the formula just to practice it right quick. We want to find the derivative of inverse secant of 5x to the 4th. So now I'm going to erase all of these things. We'll come around to finding the other 3 in just a minute. So we're going to practice using this one. We have y equals the inverse secant of 5x to the 4th. The derivative will be what? 1 over 5x to the 4th.
And we don't have to worry about absolute value.
That's right. This will always be positive, so we don't have to worry about it.
Times.
You see that? You don't have to worry about it. It's redundant to put them on. So think about it. All we need is for this to be positive all the time. If it's guaranteed to be, we don't need the absolute value. Times.
5x or
No, 25x to the 8
Times.
times 20x to the 3. Math.
But we're not done. Did you just-
Wait, where did the 20x to the 3rd come from?
Because that's the derivative of 5x to the 4th.
Oh,
That
this
changes.
is so not my stuff. Where does
We
the,
can simplify that to what?
Let's see, 4x. Yeah, 4x.
Not 4x to the 8th.
Yeah, 5. Just x. Just x.
Now we need this.
There we go. Now we need it.
This cancels with this for 4. 3 of these cancel with 3 of these, leaving 1. Now that it's got an odd power, we have to absolute value it. Did you catch that?
Yep.
Okay, so remember to simplify your fractions when you can. Okay, so I want you to think about this with me. Try to recall your trig. I want you to look down at the bottom of page 168. These are inverse cofunction identities. What we're saying is that if you graph the inverse cosine, it would be precisely a pi-halves shift of inverse sine, negative on it. In other words, because these are inverse functions, we're moving them up and down the y-axis. What does negative sine x look like? I'm only going to do this with one of them. What does negative sine x look like? Or negative inverse sine? Well, first of all, what does inverse sine look like? Goes like that and like that, right?
Yeah.
So what does negative inverse sine look like?
the other way around, just around the x.
It
Flip
flips over the y or the x?
Why? Because it would
The
flip
x.
over the x.
Inverse sine of negative x would flip over the y. Negative inverse sine flips over the x, and so this one would end up coming down like this. Well, not like that. Like this. And this one would end up going up like
Hourglass. That looks like it.
that, right? Is that inverse sine?
Okay, that does make sense. Kind of.
And then if you push that up pi halves,
Does it matter which one we flipped over?
it goes like this.
It really doesn't.
If we move it up, right? Now what does inverse cosine look like?
Yeah.
graph it. What does inverse cosine look like?
Wait, why don't we just add like 3 pi halves?
How about we just not talk about this until you get this graph?
Oh my gosh, it looks exactly like that.
It looks like this, doesn't it?
Yeah, just a little bit more steep.
So would you say that if we took inverse sine and negativized it, that means we flipped it over, that's the inverse sine, that's negative inverse sine, and then move it up pi halves, you'd have inverse cosine. So do you believe that the first line of the, and it ended up looking just like inverse cosine?
Yeah.
So you agree, do you think those others would follow suit if we drew them?
Yes. Sure.
Those are true. And if you drew them, you would get the same thing. If you negativize inverse tangent, negativize inverse secant, add pi halves to both, you're going to end up with their inverse cofunctions. So tangent inverse goes with inverse cotangent when you do that pi halves thing to it. And same with secant and cosecant. So the cofunctions are just pi halves minus their non-co buddies. Do you agree? So if I wanted to find the derivative of inverse cosine, wouldn't it be the same thing as finding the derivative of this? They're the same thing. So if I have that y equals this, that's the same exact thing as y equals this. And while I don't know how to find the derivative of inverse cosine, I can find the derivative of this. What is dy dx?
Would it just be negative cosine? Whatever the point.
It would be the derivative of this, which is
0.
times the derivative of this, which would be
Negative 1 over root 1 minus.
since it's just x, it's just 1 minus x squared.
Yeah, that's scared me.
So in other words, the derivative of inverse cosine is simply the opposite. The opposite, meaning negative sign,
Oh my
of the derivative of,
Oh, that is so simple.
and that's true of all the cofunctions. That's the reason why these three are the only ones really necessary. So if we were to I'm not going to write them down. If we were to summarize the rest, I would say if y equals inverse cosine, its derivative is this with a negative one.
Oh.
If I wanted the derivative of inverse cotangent, it would be this with a negative on it. If I wanted the derivative of inverse cosecant, it would be this with a negative on it. So there's really only three to memorize. Just remember that if the thing that you're doing has a co on it, stick a negative on the result. That's all.
That's cool.
It is cool. And that's what you'll notice at the top of page 169. With the exception of cotangent, it's kind of quirky. These are calculator conversions, though. You might want to take a look at those calculator conversions and perhaps write them down someplace on your assignment paper so that you don't have to look it up every time. Calculator conversion. So if you wanted to graph inverse secant, for example, you would graph inverse cosine of the reciprocal of what you were inverse secanting.
Oh, you can just do that?
Yeah.
Does
You
it still
can
work?
also, for any of them, you can also, as you saw down there, you can invert those, you can manipulate those things at the bottom of page 168 as well. Somewhere or another though, you gotta get her. So that you can graph those weird things that don't have buttons.
Can you put a 1 over?
No, because it does not mean reciprocal, it means inverse function. It means undoes it. It doesn't mean reciprocated. Inverse things don't. Okay, one more example, example 4. We are going to find an equation for the line that is tangent to the graph of inverse cotangent when x is negative 1. What? That's not too hard. It really isn't. We're going to follow the same rules for writing tangent lines that we always have. Only we're going to do it with these inverse trig functions. But we have derivatives for them, so it shouldn't be that bad. So this is what we're tasked with doing. Find the equation of a line that's tangent to the graph of y equals inverse cotangent of x at, is it just x? It's not a function?
Yeah.
It's just x?
Mhm.
Okay, at x equals negative 1. What do we need to write the equation of a line? A point and a slope. What do we have?
Or we have a point or half a point.
We have half a point. That's it. We got to go find the y value, and we got to find the slope, which means derivative. We need to find the y value, I think. We should find the y value first. What is the inverse cotangent of -1? That's what we have to find. That's the y value that goes with x equals -1. How are you going to do that? Inverse cotangent of... I don't think any of you got a real good feel for even what inverse cotangent even looks like. Not to mention evaluating it at some -1. What it means is find the angle whose cotangent is -1. How are you going to do that? With your calculator using these conversions. So inverse cotangent is the same thing as pi halves minus the inverse tangent at -1. You see that? To evaluate cotangent at a value, you take pi halves minus the inverse tangent at that value. So I'm trying to get you to understand you can evaluate that with your calculator if you use these calculator conversions, since you don't have a cotangent key. Pretty good. Did you do it?
2.37.
Yeah.
Divide that by, you get 2.37?
I got 2.35.
Pardon?
Oh, yeah, 2.3.
2.35?
2.356.
How could you convert that to,
Divided by.
yeah, divide it by pi? And what's the fraction? Was it
3/4.
0.75? So it's 0.75 pi, which is 3 pi fourths.
What?
Somebody help Axel,
Alright, why is 0.75 equal to 3/4?
because 0.75 is 3/4. You divide it by pi, when you add the 2.37, you divide that by pi, it gives you the fraction, which is multiplied by pi.
Okay. And pi divided by 2 minus.
Does that not make sense to you?
Here, divided by inverse tangent. Okay. I pointed at my y equals fraction. 3/4. That times pi is 3. Times pi. But we're using times pi. Because we just pulled pi out.
Because you just divided by pi, you gotta put it back in.
That's what you get minus. Okay. -1.
Do you want me to show you a little better, or do you understand that?
Show it to me a little
Yeah.
better.
Okay, so what was the irrational decimal? 2 point
2.356.
2 point what?
2.35619. 449.
Plus a bunch of garbage, right?
Yeah.
We want to know what fraction that is, so I'm gonna call that,
In terms of pi.
I'm just gonna call that x
Yes.
times pi. I wanna know what this is. What number times pi is this? So we divide by pi. We divide that by pi, that'll tell me the fraction of pi that this is, and it turned out to be 0.75. So this number right here is actually 0.75 times pi. You see that?
Yeah.
And 0.75 is 3/4. Besides the fact that inverse tangent, that's what we were using, inverse tangent of -1, in geometrically speaking, is the angle whose tangent is -1. Now, where are you allowed to look for inverse tangent values? First and fourth. Where are you allowed to look for negative ones? Fourth. What kind of an angle has a tangent of 1, or -1 actually? This one. Right? And pi halves minus that is pi halves plus 3/4. Because we were using this to evaluate inverse cotangent at -1. So pi halves minus this value, which was -pi/4, is pi halves minus -pi/4 is 3/4. That's a geometric way of arriving at that 3/4. Calculator way, is using the calculator conversion, which was this.
Right.
In your calculator, okay? Gotta remember a lot of trig, folks. Okay, so we have our point. Still don't have our slope. How are we gonna find the slope? It's gonna be -1 over
One plus e squared. 1 plus t squared. Or x squared. Which is
evaluated where?
1.
So I'm gonna say y prime, I'm gonna switch gears here. It's gonna be y prime of -1, because that's the x value, equals -1 over 1 plus
1 squared.
1. You're squaring -1. Are you with me?
Yes.
That's our m. And we write the line. Since this is irrational and this is rational, you can't combine them, so just leave it. That's good. This makes up the entire constant on the end. You can just leave it like that. If you want to find a common denominator, I suppose you could. That would be you could do that. But you could also leave it either way. Follow that? Notice what the author does. He just leaves the tangent line and slope intercept form. He doesn't even bother to simplify at all. I would like you to. I would like you to, mainly because on your ISU exams, he would like you to, the author of that, so you should practice it. Okay? 6 inverse trig function derivatives. However, if you understand the co-function idea, you only have to memorize 3. Their co-buddies are negative of those. Okay, there you go. We'll have tomorrow to work on it. There you go, Savannah. See you later. Savannah and Jacob.